So for quantum Framinius, it's quite important to know whether your root of unity is of even or odd order. And when the order is odd, and for G2, you also want it to be non-divisible by 3, then everything is more or less easy and uniform. So that's what we want to assume. So L will be a positive integer, and we want it to be odd. And for G2, not divisible by 3. And then epsilon is going to be else primitive root of 1. And then from here, we can define Lustig's form. I will denote it by U dot on top. And I want to consider it as an algebra over the complex numbers. And the thing is generated by the following elements. So as usual, we have case, we have is, and we have f's. But we have additional generators which are divided powers. Alpha to divided power L, and f alpha to divided power L. And since we are working over complex numbers, that's enough. So if we replace the complex numbers with some general ring R, and epsilon is still a root of unity, we also need to add E alpha to divided power n and f alpha divided power n for all n bigger than 0. But when we are dealing with characteristic 0 field, so this generators here are enough. In particular, that's the first difference that we see from the distribution algebra. Distribution algebra is very infinitely generated. It's not even Gaussian. This algebra is finitely generated, and it is Gaussian. So that's one pleasant difference from the classical case. But what I want to recall is quantum Framinius. And it's an epimorphism from U epsilon. Well, I can write in C, so let me continue doing this. To U dot at parameter 1. And so what this thing is doing, so it sends K alpha to K alpha. It sends E alpha and F alpha to 0. It sends E alpha to divided power L to E alpha. And it sends F alpha to divided power L to F alpha. And then also there is an important element, which is not a generator, which is this K alpha 0 choose L. So this goes to K alpha 0 choose 1. Okay. So that's an epimorphism of algebra, and this was checked by Lustig. We can simplify the life a little bit by noticing the following. So notice the K alpha to power L in U dot C epsilon is central and its square is equal to 1. And so what we can consider is the following quotient, which I will denote with superscript 1, and 1 here stands for type 1 representations. So it's going to be a quotient of u dot c epsilon by the relation that k alpha to power L is equal to 1 for all simple roots alpha. And this is precisely the quotient which will act on type 1 representations, where k's are supposed to act with powers of the root of unity. Of course, if k acts with powers of epsilon, then k alpha to power L is equal to 1, because epsilon is L's root of unity. Okay? And then Framinius gives you an epimorphism from this quotient to the corresponding quotient of the algebra u dot one sub C1. And what is this algebra? Well, we have learned in Jize's talk that when in linguistic form you specialize the parameter q to 1, what you get is very similar to the classical universal enveloping algebra. It's the classical universal enveloping algebra tensor with finite dimensional algebra, which is generated by case in relation with k squared is equal to 1. So this case, generated k, really don't interact with anybody else. And so by going to this quotient here, we really kill this case. So this algebra is just the usual universal enveloping algebra over the complex numbers. Questions, please.
Yeah, can I ask? So maybe you discussed before, but so you made this assumption on the root of unity, and there is some version for other roots of unity, which is also interesting. I mean, is there? Is it just to simplify things, or are some things?
Well, I mean, this was discussed in Jize's talk, and okay, so let's recall this. So when epsilon is a root of unity of order congruent to 2, quantum Framinius goes to congruent to 2 modulo 4. Quantum Framinius goes to the algebra of the same type, but perhaps with a different character letters. And when
so for even roots of unity, you can this type this case which square to 1, they don't decouple.
Right, but I mean that's kind of that's right. So okay, but just for the audience, as a reminder of what happens with the target to start with. So when epsilon is congruent to 2 modulo 4, the target is of the same type, but it's different form of a group. And when epsilon is divisible by 4, we get to Langland's dual of the algebra. Okay. And then, yes, so then kind of there will be, as Pasha mentioned, there will be issues with this generative k and a lot of other with case. So here you can just kill case.
Mm-hmm. And it's divisible by 4, there will be a factor of type G2, then divisible by 6, right?
Yeah. Well, yes, there is also G2 and kind of, you know.
And another question, well, you emphasize that you get this new theory in algebra, but well, I guess one of the points is that this coincidence with modular picture goes only so far, so you can have this Framinius, but you can't have second Framinius. But is that, I mean, Is there a theorem like that, or is there?
Well, I mean, I'm not sure where you're going to go from U of G in characteristic 0.
No, yeah, I mean, you could imagine there could be some, something which goes to UQ and then go. Well, I don't know.
Well, I'm not sure.
Okay.
Right. So that was
one more thing about this. In this formulas that you have, is K alpha goes to K alpha correct? Is it? For whatever reason, I thought it should be K alpha goes to 1.
well, I mean, no, K alpha always goes to K alpha, from what I remember.
I might just be misremembering. Okay.
I'll check and then I'll correct the notes if this is wrong. So, okay, so we have essentially what we are dealing with. We are dealing with Framinius epimorphism to the classical universal enveloping algebra. And that's very useful when you study representation theory, as we'll see when Jize resumes his talk. The second thing that I want to remind, or maybe introduce, is the small quantum group. So what is a small quantum group? This will be denoted by small Uepsilon. And this, by definition, is a subalgebra of U dot epsilon, which is generated by the usual generators, by K alpha to power plus minus 1, E alpha and F alpha. Simple rules. And it's a Hopf subalgebra that you can clearly see if you look at the formulas for coproducts. You can alternatively say that you have a homomorphism from the usual de Concini-Katz quantum group to the Lustig form. Guess what are the formulas? And this, so this is the Concini-Katz. And Uepsilon is just the image. And we see that as such, it's an analog of the distribution algebra of the first Framinius kernel. Now, it also has something to do with the Framinius epimorphism, namely the kernel of Framinius is generated by the augmentation ideal so Framinius here let me write who Framinius is. So it starts at U dot C epsilon and goes all the way to UG. So in particular, K alpha goes to 1 under this. So this kernel is generated by augmentation ideal of U dot epsilon. And you should view it as a quantum analog of the familiar exact sequence. So 1 goes to G1, goes to G, goes to the Framinius twist. Okay, so if you look at what happens with the sequence and taking distribution algebras, that's how you describe the kernel of Framinius epimorphism between the distribution algebras here. And then you can write a pp2 basis in this small Uepsilon. It's very similar to pp2 basis for the distribution algebra of the first Framinius kernel. Namely, what you get is like this. So I have negative root vectors times the product of generators k, say power m beta, and then product of positive root generators, where the bounds on these exponents are the following. So k alpha and m alpha are between 0 and L minus 1. And m beta, sorry, it's m alpha. And m beta is between 0 and 2L minus 1. Okay, so what we get is a finite dimensional Hopf algebra. Questions? Finally, what I want to explain is a formal connection between this quotient U super 1 of epsilon and the distribution algebra of G over the field of P. So for this, of course, to establish such a connection, I cannot work over the complex numbers. I need to work over a ring, and I want to fix, so let L equal to P be a prime with the same restrictions on L as before. And then I want to consider the following ring, which I will call curly A. It's going to be the quotient of polynomials in that with by the cyclotomic polynomial at P. So that's the ring that J was working on. Okay. And then I can define this algebra over the string as before. So nothing changes, but I need to consider all divided powers, as I've mentioned. And that's the algebra that I want to compare to the distribution algebra. For this, let's look at the two specializations of this ring here. So what's the fraction field? Well, I just invert everything, and what I get is Q adjoint epsilon. Okay, that's characteristic zero field. And then, of course, when I base change my algebra, what I get is essentially that Lustig form that I considered in the beginning over characteristic zero field, which is just as good as the algebra over complex numbers. But more interesting thing happen when I actually specialize to the interesting maximal ideal. Namely, let's notice that, so let's consider M, which is the radical of x minus 1. So I want to specialize x to 1. And when I specialize x to 1, well, I get some no, I don't need to take the radical, I'm sorry. No, wait, 1 second. Generated by p and x minus 1. So that's the correct one. That's a maximal ideal, and specialization is just fp. So when I specialize to this field, what I get is just a distribution algebra of GFP. Okay. So what's the point? I have this algebra which interpolates between quantum group at roots of unity in characteristic 0, which is this one, and the distribution algebra in characteristic P. And that's very useful because we will see it in Jize's talk, because we can use what we know about the representation theory of this, which we've learned in the previous lecture, to establish what happens for the quantum group at P's root of unity, and maybe in some bit more general roots of unity too. All right, questions, please.
Can you remind me again what you mean by as good as U, C, epsilon?
Well, I mean, it behaves the same way. It's just smaller field of characteristic 0.
It's just what?
You just use a smaller field of characteristic 0. You can further base change to the complex numbers.
Oh.
More questions? Okay, Jize is here. Jize, are you there?
Yeah, I'm here.
That's good. All right, let me stop sharing, and then Jize will be making his talk.
Okay, thanks. Why this is a black screen? This is weird. This is really interesting. Let me do it again. This is start podcast. This should work.
Sit into his lecture.
Okay, thank you for the introduction. So today I'm going to discuss with you the representations of quantum groups at roots of unity. So let's start by looking at the notations that will be used in this talk. So as usual, G will be a complex semi-simple Lie algebra, and we denote by Aij, the Cartan matrix. And the Di will be co-prime integers, such as this Di Aij becomes a symmetric matrix. And the Qi will be denotes Q to the power of Di.
Jize?
Yes.
You can hide this panel with pages.
You mean the pages on the right?
Yes. And then your writing will become larger.
Mm-hmm.
And for this, you just click at the rightmost icon on the toolbar.
Thank you.
No, yes, you can, yes.
Right. Okay.
Yes.
Yeah. Okay, great. Yeah. Then this A will be the ring of Laurent polynomials with coefficient Z and the variable Q. And U of A will be the A subalgebra of the usual quantum group UQ of G, which is generated by the divided powers EI to the divided power of R, I for I to the divided power of R, and KI plus minus 1 for I from 1 to N. And UA plus will be the A subalgebra of U of A, which is generated by the divided powers EI to the divided power R for I from 1 to to N, and R is a natural number. And similarly, we define this UA minus and UA 0 to be the corresponding A subalgebras of U of A generated by Fi, divided powers of Fi, and also this Ki plus minus 1, and this Ki comma C2 star specialized QR. And we will use the notation U epsilon Z to denote UA tensor with Z epsilon over A. So here epsilon is a non-zero complex number, and we assume this epsilon to be a primitive L through unity, where L is odd, and we assume L is greater than Bi for Li. And U epsilon will be UA tensor with Q epsilon over A. And finally, I will write epsilon I to be epsilon to the power of Di. Okay. So the first topic we will discuss today is representations of this Q epsilon. Okay. So let V be a representation of this U epsilon. So we have seen in Ivan's talk that so EI to the power of L and I5 to the power of L equals to 0. And moreover, this KI to the power of L is central in U epsilon. And we have a KI to the power of 2L equals to 1. So this fact tells us that, I should write, so it tells us that this K1 to Kn, they act on V via commuting operators. So which are, so they are simultaneously diagonalizable, and they have eigenvalues take values in the set epsilon plus minus epsilon to the power of R. So where R ranges from 0 to L minus 1. Okay. So as we have seen many times in the previous talks, that we can always tensor a one-dimensional representation. So tensoring a one-dimensional representation well allows us to look at.
You missed one.
Pardon me?
It's one dimensional, not just dimensional.
Yeah, tensor a one-dimensional. Thank you. Let me just write. right, one-dimensional representation, allows us to restrict our attention to these representations on which on which the ki to the power of L acts by 1 for any I. And we will call such representations of type 1. So throughout the talk, we will focus on type 1 representations. So here is lemma. So so let V be a finite dimensional Uepsilon representation of type 1. Then we have the following numerical result. So first of all, we know the L's divided power of EI and L's divided power of Fi. They both act nilpotently on V. And secondly, we know that this is ki, comma 0. This k, comma 0, choose L, specialized to epsilon I. So recall epsilon I is defined to be epsilon to the power of di. So they act on the diagonalizably and with integer eigenvalues. Okay, so the proof of this is more or less by computation, and I will leave it as an exercise, but I will just list out the numerical, all the combinatorial identities that will be used in the proof. So exercise, hint. So first of all, we will need this relation between this ki comma c, choose t, times ej divided power s. This equals to ej divided power s, and this is ki, and we have a c plus s aij t, and another identity we will use is this relation for the divided power of fj. So this equals to fj divided power f, and we have a ki comma c minus s aij choose t. And we will also need a relation which allows us to compute ei divided power r times fj divided power of s. And this can be written as for r as greater than or equal to t, greater than or equal to 0, I divided power s minus t, and we times this ki m2t minus s minus r, which is t, and specialize at qi. Recall qi is q to the power of di, and we times this this R minus T.
No, I think is epsilon.
You think is R, right?
Q is epsilon.
Yeah, sure. Yeah, that should be, sorry. Yeah, of course. Sorry. This, right, this is I. And this is EI divided by power R minus T. Okay, and we will also need this one. So okay, 1, 0, L times R, and epsilon is equals to R factorial, 1 over R factorial, and it's pi as from 0 to R minus 1. Here is K1, 0, L epsilon SS. Okay. So we have seen how the divided powers of EI and Fi act on V, as well as how this Ki, 0L act on V. So so this lemma motivates the following definition. Again,
Just, I don't understand the last formula. What do you multiply with?
so that is
S is okay. S is the summation. Is
S is in the sum. It's in the It's right. I apologize for my handwriting. I'm trying to write nicer. Yeah. So
also, if you rotate the iPad 90 degrees, then we'll see less of a page, but the size will be bigger, which may help. Yes.
Does this look nicer?
Yes.
Okay, great.
It's actually readable.
Thank you. It's a very helpful tip. Right. Yeah, I do see. I have more space to write. Yeah, it's much easier. So right again. So like we be a type 1 representation. So we define the weight space. V lambda to be all the vectors in V such that Ki acts on it by this scalar epsilon I to the power of lambda paired with alpha I check. And this Ki, 0, L epsilon I acts on it via this integer lambda paired with alpha I check. L specialized epsilon I. V for all I equals to 1 to n. So if V is finite dimensional, so we define the characters of V as usual. So this is sum of the dimension of its lambda weight space with this V lambda. So okay.
But there also should be a statement that V actually, if V is type 1, then it splits as a direct sum of its weight spaces.
Yes, this is exactly the next proposition that I'm going to state. So we assume V is a type 1 representation of U epsilon. Then we know that V is exactly the direct sum of its weight spaces. Okay. So again, the idea of the proof still follows from the classical case, and I would say that the only thing that we need to the only extra. So okay, I would say this again. This is as an exercise, but we will need the following combinatorial lemma. So right. So this lemma basically tells us that. So let me just write it down. So let's say epsilon. This is a primitive. L-iterative unity. Of course, L is odd. And let's say R and S are natural numbers. So we assume that R equals to R0 plus L R1, and S equals to S0 plus L of S1. So where R0 and S0 are between 0 and L minus 1, and R1 and S1 are greater than or greater than or equal to 0. Then this implies that so this RS, R choose S specialized at epsilon. This equals to R0 choose S0 specialized at epsilon, and times the usual binomial coefficient R1 choose S1. Okay. All right. So we give the definition of a highest weight module. So let V be again be a representation of U epsilon of type 1. A vector V inside V is called primitive. If EI acts on it equals to
It's just V.
pardon me?
The vector is V, not Vi.
Right, exactly. I was talking about EI instead of VI. Yes. So this is divided by power L. Acts on this V equals to 0 for any I. And we call V is a highest weight module. If it is generated by a primitive vector.
You mean primitive weight vector?
Yeah, primitive weight vector, yes.
Actually, can I make one more remark?
Sure.
Of technical nature?
Sure.
So click on the pen icon.
Click on what?
On pen.
Pen.
Pen. No, pen. Click on pen. Click
Yeah.
on it.
Yes.
Again. So you will see thickness.
Yes, I can
Choose
see.
smaller thickness.
Smaller thickness.
Yes.
I'll choose this one.
And try to write something.
Okay, this does this look nicer?
Well, I mean, it looks more readable.
Yeah, okay. I will use this thickness. Thank you.
You can also vary thickness of the eraser.
Yeah, this is the trick, I know. Thank you. So, so let's talk a little bit about the structure of a highest weight module. So if V is a highest weight module with highest weight lambda, then we decompose this into direct sum of weight space V mu, where mu is less than or equal to lambda. And moreover, the top weight space is C span of this V lambda. So I will skip the proof. It's really analogous to the classical case. Okay. So we define this Vowel module. Which I call delta Q of lambda. This is defined as defined to be this UQ quotient by this ideal, this life ideal generated by relations generated by EI, Ki minus Q lambda I. So I from 1 to n. So where this lambda is lambda 1 to lambda n in Q cross n. So this is weight. And we know that so this is delta Q of lambda is a free.
Something's wrong. If it's Q to lambda I, then it invites lambda I to be a weight.
So then I think that
You
should
can have a Vowel module for any n tuple of, you don't need them to be invertible.
Mm-hmm.
But here I suggest that lambda is a weight.
Right, exactly. Right, so right, so then I think that's just Ki minus lambda I suppose.
Well, I mean, to keep notations consistent, I suggest that you make lambda a weight.
Okay. Right, it's a weight.
No, it's just, yes, you need to erase Q with this Q of Q, whatever. It's an element of lambda.
Right. Okay.
Good.
Yeah, of course, it should be. Sorry. Yeah. Then we know this Vowel module is really a free UQ minus module. Which is generated by this vector V lambda, which is essentially the image of one, and it has a unique irreducible quotient, which I write as LQ of lambda. Okay. Of course, this is with highest weight lambda. Okay. Now we let V A of lambda be this UA submodule of LQ lambda generated by this primitive weight vector V lambda. this allows us to define the Vowel modules.
At some point, you want lambda to be dominant.
Yes, exactly. So assume lambda be dominant. Then we define the Vowel module. W epsilon of lambda to be this V A of lambda tensor with C over A. So via the homomorphism. A to C, which sends this Q to epsilon. So here is the proposition for Vowel modules. So for any dominant lambda, so we have, first of all, this dimension of W epsilon lambda is finite. And characters of W epsilon lambda is given by the Vowel character formula. Okay. So so since this W epsilon of lambda, this is a highest weight module. So we know it has a unique irreducible quotient. Which I call L epsilon. Okay. So a corollary of this, of the previous proposition, is for any dominant lambda, the dimension of this irreducible quotient, L epsilon lambda, is finite. Moreover, if one of the two following conditions is satisfied, we can derive that the character of this L epsilon lambda is given by Vowel character formula. So I will write down what these technical conditions are. If one of the following.
Are you sure these conditions will be corollaries of what you already stated?
So this condition will actually be the condition for lambda such that the Vowel module W epsilon lambda has its character given by the Vowel character formula. So that is to say, if lambda satisfies one of the following two conditions, actually the Vowel module, the corresponding Vowel module, has character given by the character of the corresponding Vowel module is given by the Vowel character formula.
Well, this you already stated.
I mean, that is, sorry, yeah, you're right. Then this is a condition for the corresponding Vowel module to be irreducible.
Which doesn't follow from what's already been said.
Right, it doesn't quite. Okay, maybe I should.
In which case, it's going to be a corollary.
It can be a corollary. Right, then. Okay, right, let me just put it into a separate proposition, okay. So let lambda be dominant. If lambda satisfies one of the following conditions. So condition A is lambda plus rho pair with alpha check. This is less than L for any positive alpha. And condition B is lambda equals to L minus 1 rho plus L of mu for some dominant mu. Then in this case, the corresponding Vowel module is irreducible. And the character of L epsilon lambda is given by the vowel character formula. Okay. So
and much of this is going to be proved later.
Right. Yes, I'm going to skip the proof of the proposition and directly go into the main theorem of this section.
But this proposition will be proved later in the lecture.
Right. Let's do the main theorem. So the theorem tells us that so every finite dimensional irreducible Uepsilon module of type 1 is isomorphic to L epsilon lambda for some lambda in plus. So I should say the proof is similar to the classical case. So we can write V as the sum of its weight spaces, and let lambda be the maximal weight. So we know that 0 is not equal to this weight vector V lambda, and this is clearly primitive. So this basically tells us that this vector V lambda generates. Okay. So then it remains to prove this lambda is really dominant. So in other words, lambda pair is alpha check is greater than or equal to 0. But this can be, so the proof of this is left as an exercise. It made use of the following combinatorial identity. So I for I to the divided power ml equals to 1 over m factorial of I for I to the divided power of L, and then to the usual power m. And also this made a previous, the proof of the dominancy of this lambda vector made use of the previous result which relates to this. So this is the first thing. The second thing is we recall that we just introduces RS specialized at epsilon equals R0 as 0, specialized at epsilon, and U times RS. Okay. So we can also construct this L epsilon lambda in the following way.
Because at some point it would be good to make a break.
How about now?
Well, I mean, if you have just maybe you can finish the section.
Maybe I can just finish a few few more sentences. So we can also define this L epsilon lambda as follows. So first of all, we define this Verma delta epsilon lambda as the quotient of U epsilon by this two-sided ideal U epsilon ki minus epsilon I to the power of lambda paired with alpha I check. And here is ki comma 0 L specialized at epsilon I, and we minus lambda alpha I check paired check, which is L epsilon specialized at epsilon I, and EI to the divided power L. Okay. Then we can see that from the definition, delta epsilon lambda is a highest rate U epsilon module. So we can just directly define L epsilon lambda as the unique irreducible quotient of this delta epsilon lambda of highest rate lambda. Okay, yeah, let's take a break.
All right, let's make a break until 5:20. And meanwhile, do people have questions?
It's not really a question. What's the main reference that we're using now?
The main reference for this section is actually this book by, I don't know, this is very embarrassing. I don't know how to pronounce the. Yeah, the name of it was, yeah. That's the section 11.2 of this book is the main reference for the first part of the talk, and in the second part of the talk we will use the APW paper as a main reference.
Which is Anderson, Polo, and Wen.
Yeah, Anderson, Polo, and Wen.
So Cherry Presley refers to this, I think it's called Guide to Quantum Groups, and it's an omnibus book about literally all aspects of quantum groups. More questions?
Yeah,
Okay.
sorry. So in the proof, it seemed like one was using some sort of generators and relations presentation of the Vowel Module. Would you mind recording what that is?
Sorry, which proof were you referring to?
That every symbol was just one of these L lambdas.
Yes, every right. This is as marked to L epsilon lambda. Are you talking about this, the proof of this one?
Yeah, exactly. So
maybe to answer the first question, we did not.
Yeah.
Actually, we'll spend some time verifying a special case that the presentation of the Vowel module by generators and relations is as what you expect. And what you expect is that it's the same relations as for the finite dimensional irreducible in characteristic 0.
Yes.
But this is unclear from what has been said so far. So what we've been using is just so Vowel modules are irrelevant for classification of irreducibles because we can use verbs. And we just need to show that the highest weight of every finite dimensional irreducible is dominant, which is reduces to the SL2 case.
Yes. 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 Okay, and then sorry. So actually, yeah, I was looking. So for the Vermas, is so the way that it was defined here was via some base change. Can you not just directly say it, just using the quantum
For
group?
Vermas, you can.
Okay, good.
For Vowel modules, it's a little bit tricky. So as we'll see in the next part of the talk, the claim that Vowel modules have a universal property as their characteristic P counterparts, it's not a trivial claim. We'll only establish it at very special roots of unity, where we can reduce to characteristic P. Classical story.
Okay, great. Thanks. Yeah, thanks.
More questions? Maybe before we resume, I want to make a comment about how, so what is it that we are going to see? We are going to see something analogous to representations in characteristic P. And there is the following kind of dichotomy, that structurally quantum groups in roots of unity are more complicated than classical objects, such as universal enveloping or distribution algebras. However, the representation theory in characteristic 0 for quantum groups at roots of unity is easier in the end than what you have for algebraic groups in characteristic P. And in the end of Jize's talk, maybe this time, maybe next time, we will see some manifestations of that. All right, so maybe we can resume.
Okay, welcome back. So yeah, actually I got the vaccine injection in the morning, so I'm experiencing some kind of side effects. So I apologize if my voice was very low or if I made any mistakes in the talk. I'll try my best. Okay. Right. So the next topic.
So I have a naive question. Would you mind scrolling up a little bit?
Sure. Like this?
Yeah. Yeah. Is it really a two-sided ideal you're killing here?
Well, the answer is no.
Okay. Okay. Great. Thanks.
So Uepsilon on the right should go.
Right.
Like so. Thank you.
Okay.
Okay. Thanks, guys. Yeah.
Right. Sure. Yeah. And right. So the next thing we are going to see is the tensor product theorem. Okay. So for any dominant weight lambda, we can find unique dominant weights lambda 0 and lambda 1, such that lambda equals to lambda 0 plus L lambda 1. And secondly, so if we pair lambda 0 with alpha alpha I check is greater than or equal to 0 and is less than L for alpha for I equals to 1 to and to n. So let lambda 0 and lambda 1 be as above. Then there is an isomorphism of Uepsilon modules. So this L epsilon of lambda is isomorphic to L of lambda 0. Tensor with this quantum Framinius pullback of sorry, here's epsilon, L epsilon of lambda 1.
No, epsilon for the second one. That's a module over U of G.
Oh, right, of course, there's, right. So we shouldn't have anything. Exactly, this is really this L lambda 1. Right. Okay. So let me sketch the proof. The first ingredient of the proof is actually the following proposition. So irreducible Uepsilon modules restrict to irreducible modules of small quantum groups.
Well, that's certainly not true for all irreducibles.
Right, but I should say finite dimensional ones. Okay.
And it's also not true for all finite dimensional irreducibles.
Right, of course, for this restricted with restricted weights. I think this is true, right. Modules. How should I say? Whose highest weights are restricted. Right. Okay. Yeah. Thank you for the correction. Right. And in the second part, we'll see how this first part, how this first ingredient will help us to prove this theorem. So we first let M to be L epsilon lambda 0 tensor with the Framinius pullback of this L lambda 1. Then as vector spaces, we see that this Framinius pullback of alpha lambda 1 is isomorphic to home. The home space of these two small Uepsilon modules, excuse me, L epsilon lambda 0 and M. So this is by first lemma. Now we see that this home space of small u epsilon of this small u epsilon modules between this L epsilon lambda 0 and M, it actually sits inside a ledger space. So this is a home as a vector space L epsilon lambda 0 and M. So these are in fact U epsilon dot modules. Then this home space U epsilon of L epsilon lambda 0 M, in fact, equals to the invariant part of this home space L epsilon lambda 0 and M as vector spaces. So right, so which is the set of all elements such that Z of F equals to so where this is the co-unit of this U epsilon. Okay. Now this actually implies that so this space of U epsilon invariants it has a structure of this U epsilon dot quotient this this ideal generated by X times Z minus epsilon Z. So here X is in U epsilon dot and Z is in this small quantum group, and which is isomorphic to U of G. Okay, so moreover, we see that we see that U epsilon dot, this is generated by EI, FI, KI plus minus 1, and divided powers EI divided power L, and FI divided power L. If we take brackets of them, this preserves the small quantum group.
May I make a remark?
Please.
Could you please scroll up?
Sure.
So, this quotient is so the C U dot epsilon, which is the same as U epsilon from above, modulo this subspace, is what you can apply to invariant elements and get a well-defined element. Okay?
Right.
However, a priori, it's unclear why this quotient is an algebra, because the ideal that we mod out is a left ideal, not a two-sided ideal.
Right.
What we are showing now is that this left ideal is actually two-sided.
Exactly. Yes. Yeah. May I continue?
Yeah, sure.
Right. So their brackets preserve the small. Oops. Small column group. So this is by a result of Lustig. So here, this UG this UG action on the Framinius pullback of L lambda 1 is the same as its action on L epsilon 0. So finally, we can compare the height weights on both sides. Oops, sorry. So so I think the idea of as Ivan pointed to me, the idea of this proof is really similar to the proof for this Steinberg's tensor product theorem in the case of SL2. So where this L lambda 0 tensor Framinius pullback of L lambda 1, we hope to show this is irreducible. Then we just look at we first look at a Lie algebra structure, and then we relate to the structure of G1 of the Framinius kernel. And I think the rough idea goes through here. Okay, so we're going to slightly switch our notations to the paper of Anderson, Polo, and Van, and see how this distribution algebra help us study the representation of quantum groups. So now our ring B will be Z of V localized at this ideal M. So where M is generated by V minus 1 and P. For some odd prime P. So we will assume P is greater than 3 if the quantum matrix Aij has a component of G2 of type G2. So B prime will be the field of fractions of B, which is essentially Q of V. And we will write K to be the residue field of B, which is Fp. And gamma will be a B algebra. So U of B will be Lurch's form. Okay. So U of B plus and U of B minus will be the B subalgebra of which is generated by this divided power of EI, respectively, that of excuse me. And the divided powers of Fi for R greater than or equal to 0. Okay. So before proceeding to any discussion, let's talk a little bit about specializations of B into a field. Okay, so let's say we have a specialization of B to a field gamma. Okay. So we split our discussion into two cases. So first of all, if characteristic of the target field equals to 0, then in this case we know this map from B to gamma essentially. Sorry, let's do just characteristic. Sorry, let's do a characteristic P first. So if the field gamma has characteristic P, then we know this map F essentially factors through this FP V inverse and localized at 1 minus V. And we can derive that the image of V must be 1. So let's do the second case. So let's say the characteristic of gamma equals to 0. Okay. So then we want to determine the image of 1. So it can be the following cases, can be the following possibilities. First of all, it can be some transcendental element over Q. And it can be some algebraic number over Q. Then in this case, so the minimal polynomial of it belongs to this ideal P 1 minus V. So that is to say 1 minus V divides divides this minimal polynomial. Let me just call this minimal polynomial f, divides f modulo p. Okay. So the third possibility is it can be a root of unity. So in this case,
like the special case of the second possibility.
Right. This is exactly it's a special case, which is a very interesting case. So I should probably say in particular. So in particular, if it is a root of unity, then it is some p2 powerful mth root of unity. For some natural number m. So this is because the cyclotomic polynomials are divisible by 1 minus v modulo p. Okay. So the next thing we will discuss is the quantum vowel module. By the way, how much time do I have? How much more time do I have?
Like 15, 16 minutes.
Okay.
So then you'll continue next time.
Okay, sure. Yeah, I will probably, continue next time. Right. So for any dominant weight, lambda and lambda plus, we define this quantum vowel module to be WB of lambda as is a U of B quotient by this life ideal. So generated by E by EI to NI. And also this Z minus K lambda Z. Oops.
I think it's the character chi lambda.
Pardon me?
K lambda. What's K lambda?
Sorry. Yeah. Thanks. And here Z is in UB0, and also this FI IMI. So where I is 1, 2, 3 into n, and ni is greater than lambda pair with n alpha I check. Sorry, pair with alpha I check. Okay. So first of all, we know this quantum Vowel module WB lambda is a highest weight module. And we know its weight space W B of lambda mu is non-zero if mu is less than or equal to lambda. So secondly, we know this WB lambda is in fact integrable. That is to say, for any element inside the WB of lambda, we can find some natural numbers which depends on this W, such that we can annihilate this W by divided powers of EI and FI. So, in particular, we can conclude that so it has a finite set of weights. Okay. And finally, this WB of lambda is finally generated over B. Okay. So let me give a very rough idea of the proof. For the first part, we can just observe that this quantum Vowel group, this quantum Vowel module is a quotient of the Vowel module. So this is U of B tensor with, oh, excuse me. Tensor with B lambda viewed as a UB greater than or equal to 0 module. The integrability of this quantum Vowel module basically follows from 1. This is very similar to the classical case. And
well, I mean, you just for the claim about F's, you just need to use the relations.
Right. Right. And the statement 3 is basically follows from 1 and 2. Okay. So the specialization of UB prime, this is B prime, tensor B with U of B, is just the usual quantum group. and the Vowel Module W WF lambda is finite dimensional.
So F is the same as B prime, right?
Right, exactly. Right, let me just. Seems. And
It's finite dimensional and irreducible.
right, and irreducible. Oops. And so we also know that this U of K, historical K, is a residual field of the ring B. This is a quotient of this distribution algebra of G of K. Ki, and we quotient that Ki squared equals 1. Okay, so because we're looking at type 1 modules, then we know that Ki's just act trivially. And in this case, Wk of lambda just naturally becomes a module over distribution algebra of G of K. And so in fact, so this Wk of lambda equals to the definition of a Vowel module using hyperalgebra that was given in the previous lecture. And its character is given by the Vowel character formula. Oops. Okay. Then as a corollary, so we know this quantum Vowel module WB lambda is in fact, this is free over B. Okay. Right, so maybe before giving any proofs, let me make a few remarks. Okay.
Well, I'm not sure what it is to be proved, because also proof of the proposition is in the statement.
Right, exactly. But I mean the proof of this really the corollary.
Well, maybe this can be explained in words that you know,
Sure.
you have a finitely generated module over a local ring.
Right.
And then the fiber at the closed point, and it has the same dimension as the fiber at the generic point.
Generic point, yes.
So this must be free.
Yeah. Yeah. In other words, we just specialize this W B lambda to B prime and K, and the corollary just follows from what Ivan just said. Okay. Right. So let me make a few remarks. Right. So so this Vowel module W of C Lambda, sorry. Has the desired universal property. When this epsilon is a p power 3 to infinity.
So, and the desired property is the same as of the Vowel module in the previous lecture.
In the previous, yeah.
So it's the universal highest weight module with highest weight lambda.
Right. Okay. So the second thing is, so this method which allows us to go from the distribution algebra of GK to the quantum group U of B. This can be pushed further. So for more details, see this paper by Anderson, Paulo, and Ben. So let me list a few examples. So we can define, excuse me. We can define dual Vowel modules via some co-induction functor. Using co-induction functor. Which actually I will not we will not introduce. And we can prove an analog of the Kamp's vanishing theorem. And we can show that in fact, there are no higher acts between Vowel and dual Vowel modules. Okay, I think I have already run over time, and I will probably stop here, and I will continue next time. Oops. Thank you.
All right, let's thank Jize for his talk, despite all side effects of vaccines.
Thanks.
Questions or comments?
So some of these things that we know kind of only when the order of the root of unity is a power of a prime, like, do we expect that just to be an artifact of like the technique of proof, or like, or is it that we expect the results to be false at other values?
They're true. You may want to exclude roots of unity where quantum group is pathological, these very small ones, like like said roots of unity for G2. There is a paper of Sven-Rion Hansen which kind of establishes Kempf's vanishing at essentially every root of unity, but it was only done like a decade later after the APW paper. And for example, if you look at textbooks like Cherry and Presley, they very boldly reference APW, although they want like odd roots of unity rather than prime powers. So definitely different techniques are required. Perhaps this is overkilling, but various things that we have are consequences of Cardan-Lustig equivalence, which is going to be discussed at some point, but I'm pretty sure that there are independent arguments.
Thanks.
To establish this basic theory. It's kind of, the literature here is a little bit, well, I mean, perhaps a more ordered set of references will be desirable, to put it this way. More questions? All right, let's finish for today, and next time Jize will finish his talk, and Jinchang is going to talk about the Cardan-Lustig category of representations of finite algebras.